Okay guys, this video is on more to do with simple linear regression and use of matrices to calculate B0 and B1. If you think up to now, okay, let me back up a little bit. First of all, you may want to pause the video, and we're going to use this very simple data set to illustrate things. I'll show you something that I've already done just to make some of the calculations a little bit easier and streamline some of this. I can get out of this and go to Microsoft Excel, and when I'm doing just basic kinds of computations, I think Microsoft Excel works about as seamless as any thing that I know of. And you can see I have the data entered. I've already gone ahead and created some things. This column right here is the x's squared. So I have the sum of the x's squared, and this is the product of x and y. So I have the sum of x and y there. Now we're going to need some of this stuff later, so I thought I'd just go ahead and make those calculations. Doing the whole fill down thing with Excel, it makes these calculations really pretty simple to do. Plus, I just don't like I don't like adding and subtracting anymore. It's kind of weird. Alright guys, up to now, if we want to define B0 and B1, which again are the estimates of the bigger, broader model. Actually, the arrows probably should be going this way. But if we want to find B0 and B1, which are the coefficients of our model, the very first thing that we've looked at in examining the theory would be the least squares approach. The next thing we did in just a previous video is we reviewed maximum likelihood estimation, and through a combination of those we see that one approach, I'm not complicated enough to, I don't know why I put that subscript in there. One approach to finding B1 would be to make this calculation, and another approach to finding B0 would make this calculation. Those are two things right here that you need to tattoo to the brain and put to memory. Guys, what I want to do in this video is I want to change the approach, and as I told you earlier, I want to look at the operation on matrices to calculate the coefficients of our model. Now, guys, we've talked many times in previous videos about normal equations. Hopefully you can read that. And it's kind of messy. And we know that our normal equations, and again we saw this in a previous video, Alright, I want to concentrate on this and not do something silly. That the normal equations end up looking like this. And I think in the previous video, actually I think it was in one of last week's videos in week 2 of 6500 in the fall 2014, we saw that we could take this and rewrite using matrices and I just want to illustrate to you that in leading up to I just have to admit I'm just not talented enough to talk and write. In leading up to the more broader application of matrices to find our B0, B1, that we can use this. Now, if I take the inverse of the matrix that I have here on the left, you should realize at this stage of the game that we can find B0 by taking the inverse of the first matrix multiplied by the end matrix. Now, if we go back to our calculations in Excel, let's just come in and replace some things. First of all, we know that this has sample size of 5. Our sum of our x's was 125. And should have got that too. And the sum of our x's squared was 3241. And the sum of our y's and the sum of our products of x's and y's. Sum of our y's was 13.8. These are GPAs. So you kind of expect a smaller. All right, so end up with this. Now, let's scoot over to R and make some calculations and review some of what we do with matrices. Now, what I've already done here is I've already put the ACT GPA in, but I've got different numbers now. I have 5, 125. So the first thing I want to do is just create a matrix, or create a string of numbers I'm just going to call lowercase a. And it's probably pretty clear what I'm doing here. I'm creating the entries for the first matrix. I'm going to call the next matrix B. And there's only 2 entries in this, and those are the entries of the column vector that we have at the very end. Now, the next thing I want to do is create the matrix. And the first matrix, which is a 2 by 2, I hope you remember this from 5500, the matrix operation. So I'm going to get my entries from A. And then I'm going to tell how many rows I want. And I want 2 rows. And then I'm going to tell how many columns I want. So I want a 2 by 2, so that should make sense. And by row, I'm actually going to put true here, because what I want is the way that the entries are presented, I want them given to create rows. Okay? Now, matrix B. It never fails that my dogs go insane when I start putting up a video. Oh well. Matrix B, I want 2 rows. And I want 1 column. And I want by row equal true. So guys, if I look at A, you can see I've got what I need. If I look at B, I have what I need as well. Now, to come up with the product here, a couple of things. To look at the inverse of a matrix, we have to use solve. So if I go solve A, what I get is I get the inverse of A. It's kind of weird. It's not intuitively clear. It's one of those things that I had to search for. So the inverse of A would be a 2 by 2 matrix, which we have there. To multiply matrices, we use, well, I'll demonstrate that in just a second. So I will call this my beta matrix, which I can find by taking the inverse of A. And I have percentage star percentage. That's the way you multiply 2 matrices. And I want to multiply by B. Ooh, that's not going to work, guys. I called that B, so let's call this beta. All right, so I've got my beta matrix, so my coefficients would be 0.65 and 0.084. Now, just to test this out, what we could do is we could do our model. And we can do what's called our linear model and look at our GPA, tilde our ACT, and look at our model. You're going to see that we get the same values for our coefficients. Now, my undergraduate students would be like, "Well, we got to learn this stuff up here," when it's our answer is this simple. Well, you guys should never ask that question because you're graduate students and we're investigating the theory behind the game. All right? So I know you would never, ever, ever question that, right? Fact of the matter is, I know you probably have, and I can't blame you. All right, guys. Next thing I want to look at, bring the blackboard back up here. Seems to want to kick out on me. All right. Next thing I want to look at is the more straightforward approach for using matrices to calculate. Well, that's an ugly calculate. Now, we're still going to get the same values. It's just a different approach. And again, I think it's a more common approach, especially when we get into multiple regression. And what we do here is we create some things called a design matrix. And we create a response vector. And we will create our coefficient vector. As I have no idea, but when I get down to the bottom there, it will not let me write. So, wow. Hopefully you can read that. That's just going to drive me insane. I can't handle that. So we're going to create a coefficient. Matrix. You know, it's kind of funny. I put these videos up with the intent of teaching my graduate classes, and then it's surprising how many people from even other countries watch these things. So, but guys, it's all about you, right? It's all about you. I put these up for you. All right, gang. Let's think about in matrix form our data. So our response vector is going to be our y. And gang, in this situation, our response vector will be this as our design matrix. Will look like this. Again, our design matrix will look like this. And then there's one I forgot, our error matrix. Well, actually it'd be an error vector. So the error for each term. And in many ways the most important is our beta vector. And we'll usually call this B. And we'll have these this notation. All right, guys. Just noticed that I only have 4% charge. Actually, I have 5% charge left. So I'm gonna. I'll tell you what. I'm gonna teach just a little bit more. I'm going to have to divide this video into two parts because I don't want to get midway and then this thing die out on me. So I'm going to go just a little bit more, and then this will have to be divided into two parts. Guys, we know that in matrix form that this is true. We've seen that before, and we know that simple algebra shows us this to be true. We also in previous videos have seen that the goal of the least squares approach is to minimize the sum of the errors squared. Now this becomes equivalent to minimizing the sum of eta transpose times eta. Now those aren't etas, those are e's. And the reason being is if you think about E transpose, E transpose is just going to be the row vector, and of course E is the column vector. And if we multiply 1 by n times n by 1, we're going to end up with a 1 by 1, which is just going to be a coefficient. Well, if we multiply the first term times the first term, we get e sub 1 squared. Taking a linear combination, we get, should be a 2 squared. And then e sub n squared is the sum of our e sub i's quantity squared. Now again, going back to this, our goal is to minimize this. So since we know that we can rewrite the sum of the e sub I squares as e sub t times e, easier to write than etas, then it would make sense that if we take e being equal to y minus x times beta, and we see the need to minimize this, then this term would clearly play an important role. Okay? So guys, I'm going to end this video, and let's just say to be continued. Again, I only have 3% charge, so I'm going to have to split this. I'm going to have to go charge my iPad before I can put up the next video. So that's it, guys.